Okay, so let me first tell you about what we are going to do today, okay, and how we are going to structure it. The very first part of today's lecture would allow us to go into vector spaces. I have flipped the entire structure a little. What I meant is initially I wanted to capture first the REF, and then the uh, particular solution part. But right now, I feel that because it would be used in the vector spaces that, and while doing the examples, I thought that I'll include it towards the end. Okay, so we'll start fresh with a new topic, which is vector spaces, and then the components which are left in the last discussion that we had, we'll cover it towards the end. So that's the entire agenda. And we aim to complete everything which is included as a part of your lecture two. You would have already seen the slides, right? Let me show it to you if you have not already. So this is your lecture two slides, and I think I have downloaded it. It walks you through groups. Some of these things might not feel very comfortable because of the way these mathematical notations are, plus the way the abstract way of writing it here in slides has been. We'll try to make it extremely simple for us to understand and then take it from there. Okay. Uh, So we will start with groups, vector spaces, subspaces, then go into some more deeper intuitions like linear combination, then span and dimensions. We'll solve some of the problems. This is also one of the important topic which eventually would have one problem from at least one problem from this lecture is expected to be there. Okay. So whatever you go through or whatever we are going through today, please do practice, and I'll be providing some practice problems to all of you. Okay, with that, let me start and let me give you an intuition of what we are going to do today, and then we'll get back to what we left last time. Okay. Yeah, Purv, go ahead.
I think you'll take up the questions later. So I had a question from the last time, so we can take it up later. Maybe we can start
Yeah,
now.
Purv. Sure, sure, sure. Okay,
Okay.
thanks. Okay, so let me give you a simple intuition of what exactly are groups and why we are starting with this topic called as groups. Okay. Groups are, essentially speaking, these are certain moves, okay, and moves applied on certain objects. Think of you are trying to do some action on certain object, and saying that if those actions do not distort the entire object and the object is still the same as some enhanced form of the object, but if the object is still the same, then we call them as group. This is a very vague definition you might hear, but let me give you a more concrete definition of what exactly is a group. Group is and why it is required. Group is bounded of two things. The very first thing is group has a set. Let's call it as a set G. Now set, all you already know that set is a collection of items, right? A collection could be of a number or a vectors or whatever, right? So let's say there is a set G, okay, and then there is a binary operation. Let's call it as, let's represent it as this. This is how they have represented in the slide. That's why I am representing it like this. So let's say there is a mathematical binary operation, and there is a set, and this could be a set of numbers. Think of it as a set of all integers, right? Set of all integers. Now, when you have a set and you have a binary operation, what does a binary operation does? What kind of binary operation do we have? Addition, subtraction, multiplication, right? Division. All of these are binary operations for us. So think of any binary operation that you have. Addition. Let's say that if we take any two objects from the set, let's say that we have a set of all integers, we call it as a G. Okay. Now, if we take any two items from G and apply the mathematical operator, the binary operator, the output should still be an integer. Okay. So there are, or the that after the transformation, whatever you do with the objects of D, after the transformation, it should look like whatever it was before. So that's the core definition of groups. Groups are certain axioms. Think of them as uh, four different axioms that we lay together such that whatever we are doing with a set, it could be a set of integers, it could be a set of natural numbers, it could be a set of whole numbers, it could be a set of vectors, it could be a set of matrices. Think of any possible thing. If you have a set or a collection of item of anything, think of set of images, and you would want to apply some operations. And what kind of operations is what I'm going to list here. If after applying those operations, the set itself is a set, I mean, and whatever the output that you get is a part of the set itself. Okay, it doesn't changes, it doesn't become something else. Then we call the entire set as a group. Okay, so we need two things here. One, a set, which is a collection of items. Second, a binary operator which can operate on them. Okay, a mathematical operator which can operate on them. So this is an abstract mathematical language that I'm talking about, but soon you will, or all of these things would start making sense. For example, let's say that there are these four axioms that we have, and the first axiom is closure. Okay, closure is combining any two elements of the set. When you combine, let's say, let me write it down. Combining any two elements of the set. Let's say that, let's call it as G. Let's say that G is the set. Okay. Combining any two elements of the set G stays in G. Okay. For example, let's say that we have a set of all integers, and the integers would be what? Let's say -7, -6, and then so on, 0, then 1, 2, and then so on, let's say up till infinity. Let's say that this goes from infinity to infinity, right? So you have this set of integers. Now take any two of them. Okay. Right now I have taken 1 and 2. Let's combine them. Okay. Combining them as in you use any of these mathematical operator that we have. Let's say that we use the mathematical operator as plus. So 1 plus 2, when we add two things together, or when we combine two things together, the output is 3. Now, is 3 a part of the set itself? Yes, right. So 3 is a part of the set, hence closure is valid. So closure is valid in a set of integers. So this is the first axiom that you have. Combining any two element and basically you can think of combining any two elements and generating a third element. If we are generating a third element, and that third element needs to be a part of the set already. Okay. So you are not combining anything. You think of it as you are combining milk and water. You are making it a solid. No, that cannot happen. If you are combining two liquids, the output would be a liquid itself. Okay, and that's how you can understand it. Now the second thing is associativity. Associativity. What is meant by associativity is if you combine things. such that grouping doesn't matter. So let's say, for example, you take three items from the set of integers. Let's stick to set of integers just for the sake of making you understand it. Let's say that we have a set of integers and we are applying all these axioms on the set of integers. Okay. Now, associativity says when we take three items from the set, let's say A, B, and C. Okay. It doesn't matter how we combine them. Let's say the operation that we are doing is a still addition. Okay. It doesn't matter how do we group them or how do we combine them or in what order we combine them. We first add A plus B and then we add the resultant of A plus B with C. It's exactly equals to we combine A plus B plus C, wherein we combine first B plus C and then add the resultant to A. So the order of combination doesn't matter. If that doesn't matter, it's called as associativity. Now, if you think of, let's say I have three different numbers here from the set of integers, right? Let's say I have 1, 0, and 5. This is A, this is 0, and this is 5. If I if I add 1 plus 0 and then later add 5 to it, the output is going to be 6 itself. Same goes on here. If I have 1 and I first combine 0 and 5, the output still will be 6, right? So associativity basically tells you grouping doesn't matter. It doesn't matter how you are grouping and combining things. Okay, how you first group them and combine and then group certain other things and combine them and then add them together. The output is always going to be the same thing and the part of the set itself. Okay, now if you see the output in both the cases is 6 and 6 is already a part of the set of integers, right? So this is associativity. Third is identity element. Identity element. So there is a do nothing type of a thing in every set. Okay. For example, in this particular set, think of what is that element that you have in this entire set of integers. Let me rewrite this set of integers. Let's say -6, -5, -4, -3, -2, and this extends up to infinity, right? -1, then 0, 1, 2, 3, and then it extends up to infinity. Now in this set, let's say we call this set as G. Okay. This is a set of all the integers. Now in this set, is there an element that we can combine with other element, but it doesn't affects the initial element which is getting combined? Is there an element in this set? Do you see there is an element which gets represented as an identity element, meaning it doesn't does anything to any of the existing members of the set? Do you see any of such element when we combine them? Let's say we are sticking to addition itself. Okay, when we use addition and we use two numbers, let's say A and B, and we are free to choose any one of these numbers as A, any one of these numbers as B. When we choose A and B independently and we add them together, is there any number here that you see in set G that will not affect the first number? Or let's say we call that identity element as B. Is there any number that you see there? Zero, right? Exactly. So right now, zero is let's say, for example, this is 3. 3 plus 0 would be 3. Now, there has to be an identity element in the group. Okay, which means that there has to be an element which does nothing, which it is like uh, it it is just there as a measure of uh, you can think of it as you have origin, right? And I'll tell you why this is important from vectors point of view. Think of two-dimensional system. Okay, you are still looking into scalar numbers, but think of two dimensions. This is dimension number one. This is dimension number two. Now you already have a zero place here, which is called as the origin, right? Now origin helps you find out in which direction, in which orientation there are vectors aligned. Okay. If you do not have a place of reference, origin, you cannot say this vector is aligned to the second vector at a particular angle theta, because you are measuring everything with respect to the origin, right? You will never be able to say this vector is 2 units away from origin. You will have to first define that there is an origin, right? Same way of saying, you can say that this number is 3 units away from zero, right? So you have a point of reference as zero, and that's why identity elements are important, right? The fourth part is inverses. Inverses are, if there are, let's say, for every element that is there in the set, there is a partner to it, okay, which undoes the effect that the element does. So let's say there is an element A, or a number from the same set. There is a number A. There is its inverse which resides in the set itself, which undoes that part. So let's say the number is 3. What do you think? Let's say, for example, if I am taking the operation as addition itself, okay, what is that number that can get combined with 3 and make the inverse of what 3 brings in? Is there a number in this set? Minus 3, right? Exactly. So 3 can combine with minus 3 and produce nothing, right? So there is an element, there has to be an element, for example, there has to be an element which we call as inverse, that should get combined with the actual element that we have taken and produce our point of reference or zero. Okay. Now these four identities that we have discussed just now, that's closure, associativity. As closure is combining any two things results in a third thing, and that third thing would be a part of set itself. Associativity is grouping doesn't matter. There has to be a point of reference which does nothing to all the elements of the group. There is an element which actually does the reverse of what the chosen element does. Okay, so let's say we have chosen A, and there has to be a minus A in this particular case when we are doing uh, addition, thus such that it just does the reverse of what we are doing. Now think of multiplication. Okay, let's think of, we were discussing about addition as the binary operator. Let's think about multiplication. And let's say that the group is still a set of integers. This operation is multiplication. Now, for multiplication, what would be the inverse? For multiplication, what would be the inverse? Right, exactly. Division. So exactly. So let's say, for example, if you think about, if you take a number 3, okay, and you divide it by 1 by 3, okay, let's say, for example, whatever effect 3 does, 1 by 3 does exactly opposite effect. Okay, hence there is an element which does the unders or reverse of what 3 does. Okay, same is, now think of identity element. What exactly this is about inverse. What is an identity element in for multiplication over integers? What would be the identity element? 1, exactly 1, right? Because if you think of, when you multiply 4 with 1, it's going to be 4. When you multiply 5 with 1, it's going to be 5. So identity element for multiplication is going to be 1, right? Now, for all the other things that you have, associativity, it behaves very similarly. Let's say that associativity, you have A into B into C. It doesn't matter how do you combine A and B. Let's first take the product of A and B and then the resultant product with C. It is almost equal to We keeping A aside and first taking a product of B and C and then combining it with A. So it is always going to be the same. Okay. And the first one was closure. Closure was just saying when you combine two things and you get a third thing, this third thing has to be a part of set itself. So let's say that you have 7 and 3, you get 21. 21 is a part of set of integers, right? 21 itself is an integer. Why is it important? Think of psychology. We are living in three-dimensional world. Okay, I mean, I'm going slightly towards something which might not be very intuitive to all of you. Think of all the operations that we are doing. There are certain group axioms that are defined to us. Whatever we do, we would always stay as human, right? Whatever we do, irrespective of in whatever state, we can multiply, we can reproduce, we can die, but we would always remain human. We cannot become more than a human, right? So all of these properties of the groups, they are just saying that if you're playing with a set of numbers, the output is going to be a number, and that number can be an integer, it can be a whole number, it can be any other thing, right? When you are playing with a bunch of vectors, the output is going to be a vector. Okay. When you are playing with a bunch of tensors, the output is going to be a tensor. When you are playing with the matrices, the output is going to be a matrix. That's why all of these properties, closure, associativity, these are just kind of actions. Think of this as you are trying to combine something in some way, right? These are certain actions that you are taking on some of the numbers that you have already taken as a set. So after doing all the moves, all the action, whatever you are getting is the same thing. Think of any of these axioms. Every time, whatever you do, it's going to be the same thing, right? It's going to be an integer, it's going to be a number. So these things are also important from the point of view of vectors as well. And this is the hidden hierarchy that you all should be learning. Now, the hidden hierarchy is we start with groups. And you have just known what exactly is a group. Group gets operated on a set with a binary operator, and this binary operator nothing but you already know what different types of mathematical binary operators are. Basically, you can think of it as a way of combining the elements of the set. Okay. Now, groups are basically how do we combine the set? It tells us about how do we combine the elements of the set, I would say. The elements of set G. Okay, let's say that there is a set, whatever set it is. It could be integers, it could be a set of vectors or whatever, right? Group says, how do we combine the elements of set G? Now, then there is another thing which is called as abelian group. Abelian group is what if the order order doesn't matter. Okay, you already saw that the order of a grouping doesn't matter in associativity, right? But if order doesn't matter, let's say for example, if I multiply A with B and it's exactly similar to B with A, when we take A first and then combine it with the B, and when we take B first and combine it with A, if that is exactly same, then the group is called as abelian group. Okay, but if A with B, combination of A with B for a set, okay, for a set, and the combination of A with B is not equals to B with A, then you call that set, or you call that set an operation that you're doing, basically a multiplication operation in the set, that you call them as non-abelian group. Abelian group. And do you know any of those groups which actually has this property intact? Do you know anything of this sort? Matrix. Exactly. So you have matrix, think of two matrices. Think of two matrices. 2, 3, and both of them are 2 cross 2, for example, right? 2, 3, 1, 4. Okay, let's say this is matrix A. And then you have another matrix, let's say 3, 5, 1, 6. When you combine these two matrices, the output, whatever the output is, okay, is that output equivalent to combining 3, 5, 1, 6 and 2, 3, 1, 4? This is your matrix B, this is your matrix A. So when you combine A and B together, and both of these are matrices, and when you combine B and A together, both of these are matrices, are the outputs going to be the same? The answer is no. Reason being, you already know that every matrix does different type of transformation. In the first class, I told you a matrix can do shearing, rotation, stretching, right? All of those things. Same, this can also do shearing, rotation, stretching. For example, let's think of A does some stretching, okay, and B does rotation. Okay, so what you're saying is we first stretch and then rotate. Is that going to be equivalent to first rotate and then stretch? Okay, so or let's say that first rotate and then stretch, is it equals to first stretch and then rotate? It's not going to be equal. I mean, I can show you intuitively as well on the transformation side on the same application that I developed. But you do it there, and then you will be able to see that when you multiply two different matrices, it doesn't gets equal to multiplying them with a different order, keeping the first and the at the second place, second at the first place, and the second on the right hand side, right? So matrix multiplication is non-abelian group. Okay, and non-abelian group, by non-abelian group, what we are saying is orders do matter. Okay, when for non-abelian group, orders matter. So when orders matter, we call those groups as non-abelian group. Okay, we started with groups. We went to abelian group where order doesn't matter. Then we define non-abelian group. Because why did we define non-abelian group? Because we have to play around with matrices as well in this entire linear algebra, right? Then we are moving to vector spaces. Vector spaces. Now, vector spaces are, what if, think of it as, what if objects are primitive directions? Now think of why we are moving from groups to abelian group and then moving to vector spaces, because all the things that you have learned in groups, they all get applied to vector spaces. The only thing which we didn't had there in the groups definition is scaling. Okay, scaling is what we did not had there. So vector spaces along with the four axioms. Remember the four axioms that we had? Along with the four axioms, if we add scaling to it, we get a vector space. Okay, vector space is again, you have a set and you are trying to combine the set such that you get something new, right? Now set has these four different properties. One is identity, then inverse, then associativity, then closure. Along with it, what if I have a new property called as scaling? What do I mean by that? Now this is what makes vector spaces really important. We will concentrate on scaling first. Okay, think of think of any vector. Firstly, uh, a very intuitively understand that vector spaces are nothing special. These are the places where vectors reside. Okay, these are um, no, I would say abstract elements in this course. Vector spaces are the places. Let's say you reside on Earth, right? You reside on Earth, you have a particular location. Every particular individual on this planet, they reside somewhere. They have a fixed location. Okay. So same as vectors. Vectors do reside somewhere, and that place is called as vector spaces. Okay. Now the vector spaces can be uh, a three-dimensional thing, like it can be an R3. When I write something like R3, understand that it's a three-dimensional world, 3D world. So the world that we live in, the earth that we live in, is a three-dimensional world, right? But vectors can reside in one-dimensional world. They can reside in two-dimensional world. They can reside in three-dimensional world, or they can also reside in n-dimensional world. Okay, we can have, for example, we can have a vector which is basically a scalar, like a number 2, and we can have a vector. Let's say you have house prices 2 crores and the size of the house 2000 square feet, right? We have the house price as 2 crores, 2000 square feet as the size, and let's say number of bedrooms as 3. Now we have three elements to it. That's why three-dimensional. Right? N-dimensional would be house price is 2, 2000 square feet, 3, no bedrooms, and then so on. There are n elements to it. N elements, right? So this is one-dimensional vector, which is a scalar, two-dimensional vector, three-dimensional vector, n-dimensional vector. Now, all of these vectors, this vector resides in one-dimensional space, this vector resides in two-dimensional space, this in three-dimensional space, this in n-dimensional space. So we have a world defined where every vector lives. Okay. So we can have a three-dimensional space wherein a three-dimensional vector can live. So those spaces are called as vector spaces. Now, coming back to scaling part, okay, what is meant by scaling? Scaling is, let me zoom it a little up. Okay, scaling is, what do we mean by scaling is when we have a vector, let's say that we had a vector 2000, 2 crores and 2000 square feet. Okay, or we can write it like this as well. 2 crores, 2000 square feet. Now, if we scale this vector, okay, what do we mean by scaling is we multiply it with a scaling number. This number can be any real number. Now think of lambda is equals to 2. When we take lambda is equals to 2, in that case, the output become 4 and 4000. Right. Now, from visual intuition point of view, think of it as these are the two dimensions that you are working with. First dimension is the price of the house. It could be 1 crores, 2 crores, 3 crores, 5 crores, 6, and then so on, right? It could be, let's say, 500 square feet, 1000 square feet, 1500 square feet, 2000 square feet, and then so on. Okay. Now you have a 2 crore house at 2000 square feet. Your vector is here. Okay. Now what we are saying is when we scale this vector, scaling as in when we multiply this vector with a number 2, it gets shifted to a new point. Now this is where the new point is 4 and 4000, right? So you have 4 somewhere here, or let's say 4000 somewhere there, right? So it will get scaled like this. This is the new point. This is 4 and 4000, right? So scaling is now vector spaces has a new thing added up other than the 4 axiom. It says scaling, but scaling also has to be enclosed. Okay. What do we mean by enclosed? You remember there was a closure property. Okay. Closure property was saying whatever you do with vectors, okay, whatever you do with set, let's say we have a set of vectors and all these set are two-dimensional vectors, and these are the sets, let's say 2, 4, 5, 6, 8, 10. These are two-dimensional vectors, right? Let's say that these are three different vectors in the set. Okay, now this is the set G. We can apply any of those operations on this set. Okay, now you would need to see whether all the 4 axioms are actually valid in this particular set or not. Okay, obviously there is no zero, hence this is not a valid set. But think of it as, can we scale these numbers? And if we scale these numbers, what would happen to the scaled part, let's say if we scale 2, 4, if we scale 5, 6, if we scale 8, 10, in this particular case, if we scale 2, 4 itself, let's say if we multiply it with 5, okay, the output would be 10 and 20, right? The output would be 10 and 20. Now, we said a group, okay, a group is a set of items, right? A group is a group if it is able to obey the four rules. The first rule was or the other four rules that you have. But apart from that, there is one new rule which we are saying is scaling. Now, scaling says when we scale a vector, it has to be a part of the group itself. Okay, but here in what is happening, we are having only a group of these three vectors. First, I scaled the first one with 5. I have got a new vector. It still is a vector, but outside the scope of this group. Hence, this will not be called as a vector space. So for a vector space to be called as a space, a valid vector space, apart from the four axioms that we had, okay, the scaling also needs to be enclosed. Actually, out of these four axioms, the two most important axiom are addition, okay, and zero element. If you have addition enclosed and there is an origin in the space in the set and the scaling is also enclosed, then we combine them and we call that space as a valid vector space. Now get an understanding using an example. Think of you have a set G, and that set G is all possible two-dimensional vectors. Let's say that I'm taking all possible two-dimensional vectors, and those could be 0, 1, 0, 0, maybe let's say 100, 10, and so on. Whatever you can think of, all possible two-dimensional vector. Okay, that is G. Now think of the three things that I'm talking about. First, addition. Addition. If we add any two vectors from this group, what is that output going to be? Is the output going to be a part of this group? Because we have already assumed that it is the list of all possible two-dimensional vectors, right? So this is a set of all possible two-dimensional vectors. It's just that I have listed only three here, but think of everything is included here. Okay. Do you think when we add any two of them, addition, which we heard in groups, right? When we take two elements from here, add them together, let's say the very first two elements, 0, 1 and 0, 3. Let's say that this is 3, right? And 0, 3. Do you think when we add them, we'll get an output which will stay in the same group? That's right, right? Because I was saying this set is infinite number of two-dimensional vector that you can think of. They are all a part of this. So the output 0 and 4 would still be a part of this set, right? So we call this as output is enclosed, okay? Or the closure property of addition is respected here. Now think about scaling, okay? Scaling as in take any two vectors from R2. Now let's say that we take some different vectors, let's say 2 and 10. Okay. If we scale them with a number 2, what would be the output? Output would be 4 and 20. Now 4 and 20, because we said that the set is all possible two-dimensional vector. This is already a part of that set, right? Similarly, if we scale it with -1, I will get -2 minus 10. Okay, in that case. But think of what is happening here. What is happening here? This is the visual intuition that you should be able to get. Okay, let's say that in addition, we are talking about this particular thing. Let's say this is vector A, this is vector B. Okay, think of them as these are two different vectors. When we add these two vectors, we get a third vector, maybe C, right? Now this third vector is still a part of this space, this entire space, right? Hence, addition of two vectors is a vector of same type. stays in the same space. Hence, addition is enclosed. Now think about scaling. When we scale vector b, and I multiply it with a positive real number, it gets scaled like this. When I multiply it with negative real number, it gets scaled in the opposite direction, right? Think of this as 210 somewhere would have been here, right? But when I multiplied it with minus 1, it moved back. Minus 2 and 10 would be somewhere here, right? But it still is a part of the space, right? So addition and scaling, if both are enclosed, okay, and then we have a zero or origin as a part of the space. Right now you see that the origin is a part of the space. So firstly, addition is enclosed. Everything, every combination that you do, however you combine vectors, the output vector are going to be a part of this space. Whatever way you scale the vectors, those scaled vectors would always be a part of the space. For example, just to help you understand that, go to on the same page, linearalgebra.info. Okay. Now think of it as scaling. This is the operation, right? So you have a scalar number. Right now it is 1.6. This is the vector 2.2 and 1.1. This is that original vector in yellow. Now, when I change the value of scaling number, a very positive number, it gets scaled out to a very large value, right? When I scale with a negative value, this is what would happen. But it is still a part of this entire vector space that you are able to see, right? You are able to see that this space and it's a part of the space. It's not leaving that space. So scaling is enclosed operation, right? If you are doing a scaling of a two-dimensional vector, it would always be a two-dimensional vector. Okay. Same goes with addition. Think of it as you have two different vectors here. Okay. This is the first vector, which is in blue on the right hand side. This is the second vector, which is this. Now, once you add them together, you get this purple or pinkish vector that you see, a plus b, right? Now, let's say I'll come back to you, Dheeraj. Let's say when I change a and when I change b, the output vector that you see as a plus b is still a part of the space. I'm just changing one by one all of them, both of them, right? So you are able to see that whatever I do, if I change a or if I change b, right, the output vector is not going outside this two-dimensional space. It is going to be a part of this two-dimensional space. It is not going into a three-dimensional world, right? If that happens, then your enclosure property holds, sorry, it breaks. Okay. So this is called as vector addition, and I'll come back to you. Some of you who have raised your hands, these two things are called as vector. Remember that these are the most important things: vector addition, and scalar multiplication. These are the basic fundamental things that give rise to almost entire linear algebra. Okay, because you have vectors, you can add vectors, you have vectors, you can scale vectors. Okay, that's why it is called a scalar multiplication. When you add them, scale them, then you do a lot of things in linear algebra. Yeah, I'm coming back to all of you. Out of space, as in you cannot go beyond two-dimensional space. You cannot go to the third three-dimensional space. You cannot go into a lower dimensional space. That's what is meant by out of this space. You cannot bring. Let's think of it as whatever we human do in this three-dimensional world, we cannot go beyond this three-dimensional world. We, the beings of two dimensions, are trapped in two dimensions. I mean, I'm just saying that philosophically, but think of this as. Go ahead, go ahead.
Yeah. Hey,
So,
hi.
sir,
So,
hello.
Yeah, yeah.
uh,
So,
so
when
yes, yes. Go ahead.
So when we do the matrix multiplication also, so it will be also under inside the set, right? So it's also um
It's a set, but it's a non-abelian group type of a set.
okay. So it should be abelian also.
No, see, abelian or non-abelian are two different things that you have heard. Okay, groups is what we started with. Groups has those four different axioms. Okay, and then we said that there could be abelian and non-abelian. Now matrices, they get resulted because of vector scaling and vector addition.
Hmm.
Now these vector spaces are mostly going to be non-abelian if you talk in terms of matrices.
Um,
Okay.
So, sir, matrix will never be a part of abelian group, right?
Matrix will never be a part of a Abelian
Oh,
group. That's right.
sure.
That's right.
Thanks.
So my question
Sir,
is regarding the closure, Saurabh sir. So as you have given the example of -7 to it is ranges to the +7, right? And you have given example that 1 plus 2 is it is within a limit within a group because of that it is a closure, right? What if I
Mhm.
take an example of 7 and 6? If I
No,
add it,
all right. What I was saying in that example was we can, I took -7 and 7. I mean, let's say this, I said that it goes to infinity. This is the infinite integer set. Okay.
okay,
Both on the positive and negative side.
okay, got it, got it. Okay, I thought it is the limited to the
No, no, no.
minus
It's a,
seven.
if it is
Okay,
a limited, firstly, I understand
yeah,
that. If it is a limited set,
yeah.
anything, if it is a limited set, it cannot be a vector space or it
Oh,
cannot be a
okay.
group itself. Now,
Yeah.
just before some of you speak on a thing, tell me this. Let's say that this is two-dimensional world that we have.
Mm-hmm.
Okay, and this will clarify some of your questions that you have.
Mm-hmm.
Let's say that there is a line. There is a line which doesn't passes through the origin. This is that line. Okay,
Mm-hmm.
and do you think this particular line is a vector space? Now think of any vector which can fall on this line.
Mm-hmm.
Do you think addition of these vectors, because let's say this is a one-dimensional line within this space, okay? Now this space, the green space, let's say that this vector is whatever this vector is, any of those vectors that you can think of, right? Do you think it would be a vector space? What are the three things important for calling a space as a vector space? Addition has to be enclosed, right?
person identity will
Scale,
not be satisfied.
scalar,
Right.
and identity zero is not a part of this,
Mm-hmm.
right? So because zero is not a part of this cannot be a vector space. Now think of a line which goes through origin. Okay? Now is it a vector space? Now think of any vector which is, let's say for example, we have a vector 1 1. We have a vector 1 comma 1. This is a vector. If and then we have a vector, let's say 4 4. Okay, here I will come back to you, Priya. 4 4. Let's say that these are the two vectors that we have. This is the first vector, this is the second vector. When we add these two vectors, the output is going to be 5 5, right? So let's say for example, we extend this, and let's say that this line is infinitely extended up to infinity. So
Right.
the output is going to be a part of this. Think of any possible scaling. Let's say I scale 1 1 with a negative number and scale 4 4 with a positive number and then add them together. The output is still going to be the part of this green line.
Mm-hmm.
Just for example, let's say that I scale 1 1 with -1. Okay. And then I scale 4 4 with 2. Okay. Output is going to be -1 plus 8 8, which is basically 7 7, right? Now the 7 7 would be somewhere here on the upper side. Let's say that this is that point, but that point would also be a part of the line itself, right?
Right.
Because adding and scaling vectors, you are still being a part of this space. Hence this green space is a vector space, and it also has the zero element, right? It's a vector space. Now, this is a question for all of you, which was asked in one of the exams. Okay. So let me, and it was asked by the same professor who is heading the group. So let me just say that, do you think this particular space, which is confined between, let's say, x1 and x minus 1 and y minus 1 and y1. So let's say x in between 1 and less than, sorry, minus 1 and 1, and y space is confined between minus 1 and 1. So you get a space which looks like this. This is the square, right? Do you think this square is a vector space?
No, it's not.
Any other answer? Anyone else?
No.
Why?
Because it has limit. It has
Scaling.
limit.
Scaling of any of the vector will take it out of the space.
Exactly. Scaling of any of the vectors, let's say this is a vector, let's say this is a vector 1, 1. If you multiply it with 4, it will go beyond this region. It will come here, right? Scaling or any two vector, or could be adding of two vectors, may result in a new vector which is here. Now, a new vector which is outside the space, the enclosing property or the closure property is not valid here. Hence, this space will not be called as a vector space, right? So for a space has to be a vector space, it has to obey three important laws: scalar multiplication. I'll come back to your questions. Scalar multiplication has to be obeyed to be enclosed. Okay. Same goes with vector addition as well. Vector addition has to be enclosed, and origin has to be a part of the space. Has to be a part of space. If you have these three things valid, scalar multiplication is enclosed, vector addition is enclosed, and origin is a part of the space, then you have a valid vector space. Now ask your question, go ahead.
So, sorry, sir, I have a doubt. So, if x and y is less than 1, any number, if you multiply it with, it will be less than 1 only, right?
No, I was saying that the space is enclosed. You can define any vector within this space. This space is enclosed. This space is
Okay.
within. Now you
Okay.
can take any vector. Let's say I took the vector 1, 1. Let's say that this is the vector 1, 1.
Hmm.
Actually, I drew it wrong. So let's say this is the vector 1, 1, right? This is the
Yes.
point. This is a part of the space. But as soon as we scale it slightly, even if we multiply it, it will be 1 by 1, 1.1. It will go outside the space. It will be here. Okay.
Okay. So, if we are saying the range is like within 1 and minus 1, means
Right.
the samples would be also taken from that only, no? Or
Right. The samples will be taken from that only, but we can scale those samples, and we do
yeah,
not have limit
can
to
we take
scale
one
them.
example? Huh? Can we take one example like which is less than xy less than 1 and
Let's
then
say
multiply?
let's say that this is that. Okay. Let's say that
Okay.
this is minus zero point 0.5.
Hmm.
Okay. Sorry, zero point 0.5 and minus zero point 0.5. Okay.
Yes.
And
Yes.
minus zero point 0.5 is this, and minus zero point 0.5. Now let's say that we multiply it with 10. What would
Yes.
happen? The output would be 5 and minus 5. The output is somewhere here.
Okay. 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 Okay.
Right.
Got it.
Sir, I have two things to ask here. One thing for all the audience, please respect the hand raise, the way people are raising hand, and let's follow the cue. And second thing is, when we say this vector space, and you showed in this example, it's one is to one is means that if x is between minus 1 to 1 and y is minus 1 to 1, so it's not a vector space. So is it's a relative if let's say my vector sets are small and some multiplication stays within that range, because scalar multiplication you don't know means is it we define this vector space beforehand, or it's a imaginary concept which includes the whole space?
It is an imaginary concept. You can think about it as this came into being because for all the maths that you are doing or you would want to do need to obey certain rules. Okay. So people brought in this concept that if you are trying to combine things, those things has to be things itself. They cannot become any other thing. Let's say if you are trying to combine liquid, they cannot become solid. If you are trying to combine force, they have to be force. If you are trying to combine numbers, they have to be numbers, and they cannot go beyond. There is a limit. Let's say numbers can be a numbers, but there is a limit. If you have a small enclosed set, you cannot, and you are saying that you cannot go beyond that set, that entire space can never be a vector space, because if you do not have a specific limit of scaling, okay, you can scale any vectors or and any add any numbers, then there are chances that the output might get outside that enclosed space. Hence, then those cannot be called as a vector space. But logically speaking, these things came up because we wanted to enforce certain rules, how the entire maths would work when we are trying to combine vectors, and when will it fail. So you already know that when will it fail? When you have a enclosed group, when you have a small group, think of it as this is just a simple example that I gave, right? I also took a simple example as three vectors, one, two, let's say three, four, and let's say 0 is also a part of it, and let's say that four vectors, 4 and minus 2, let's say that these four vectors are there. Can these four vectors, these are set, let's say these are part of the set G, can these four vectors be a part of firstly forget about vector space, can they become a group itself? Okay, the answer is no. Reason being, you cannot you cannot add two things and then still stay within this set, right?
Mhm.
So when you have a very small set, when you have a small region, when you have a small space, in that case, when you start combining things, you might go out of that space, and hence the limits of groups or vector spaces will not hold true. We have to consider our vector spaces infinite enough so that we can do, even if we are not able to think about them, but still whatever we are doing, it we think that it remains within the space. Okay, so that's why we think of infinite vector spaces.
Okay, so Miss, until unless my vector multiplication or addition, let's say it's a 2D space, it stays in 2D, it's part of vector space, everything is vector. So I need not to define that beforehand in any problem statement,
Right,
right? It's
right,
considered it's minus infinity to plus infinity,
right,
right? Okay,
right.
yeah, thank you.
Yeah, go ahead. Next, please.
So, sir, as you have taken that example where the vector space is infinite, so in that you have give three properties, which is addition, zero element, and scaling also enclosed. So why the
Right.
multiplication is not a part? So this I
We
have
are
not.
scaling is multiplication. Okay. When we are saying
No
scaling,
scaling, no sir, matrix
Met
multiplication I'm asking.
vector multiplication, that is a dot product that you will learn later on. Dot product is different from what we are. Let's say when we are combining vectors, you cannot combine two. You cannot multiply two vectors. You just can take products as dot products, and there are rules for doing them. Let's say, for example, when you have two vectors, 1, 2, and you are trying to multiply it with 714. Okay, you can, the only way you can multiply is the x. Let's say this is the x dimension, this is y dimension. You can combine x dimension of first one with the x dimension of second one. You can combine y dimension of second one with the y dimension, sorry, first one with the second one. But if you think about, when you take the dot product, the output is what? 1 into 7 is 7, plus 2 into 14 is 28. When you take a dot product, the output is what? 35. 35 is what? You had taken two vectors, okay? You combine them and you basically took a product of them, dot product, and you got a scalar number. Okay. The very first thing is whatever you are doing with your vectors, if the operation, the way of operation results in a vector that is a that obeys the laws of group. Right now, we are not discussing about multiplication because multiplication doesn't obeys the laws of the group. We are having dot products. Multiplication as in we we had different types of mathematical operations. We said that we can add, we can multiply, we can subtract, we can divide. But herein, we are only speaking about vector additions and scaling vectors, not multiplication, not division. Okay, because we know that if you multiply the vectors and there is only one way to multiply them, that is to take a dot product, and dot product gives you something which is a scalar number, right? So that is itself not bounded. So we are not talking about the binary operations of multiplication or division here in vector spaces.
So sir, it
Good.
can give a scalar or matrix. So both it can give after doing multiplication. So that's why we are not considering it.
So it cannot give a matrix. When you multiply two matrices together, let's say when vectors are arranged in a matrix and you multiply two matrices together, in that case the output would be a matrix. And you already know that matrix is an abelian group.
Okay.
Okay. So
Yeah.
matrix, when you multiply vectors, vectors will give you a scalar output. It will not never give you a matrix output.
Okay, understood.
Yeah, we'll go one by one. Okay. Whosoever has raised first, Kumar, I think Vivek Kumar,
Yeah,
go ahead.
yes, sir. So in the previous example, I have one doubt, like how do we define the space? Like we are saying that previous example is not a vector space. Can you go up a little bit? Left side, left side, left side. This one.
Mhm.
So here we are saying this vector is not in a vector space, but how we define the space here? What's
Okay.
the
Think
space?
of it this. We are defining firstly, let's say that I told you vector space is nothing but groups, all four properties of groups along with scaling. Okay. One new thing that we are defining in vector spaces is scaling. Now think of whether all the properties of groups are valid here for these three vectors, these four vectors. The properties of groups are not yet valid, even for vector scale space itself. The three important thing that I told you, the vector addition, scalar multiplication, VASM, and zero vector. Zero vector is there. This is here already, right? So you already are able to see that zero vector, which is fine. The zero vector is there, but can you do vector addition and still be a part of this set? When you combine these first two, 1 plus 3 is 4, 4 plus 2 is 6. The
Mhm.
output becomes 4 and 6. Now 4 and 6 is not already a part of these four vectors. Hence, a space only governed by these four vectors will not be a vector space.
But if we consider entire space, means
No,
from plus
these
infinity to
uh,
minus infinity.
that is why I was telling you as an example. When you have a confined space, a small
Okay.
space, think of a small space where only a few things are there. You here in this example also you are looking into a confined space. Okay, when you have a confined space, there are chances that when you add vectors or scale the vectors, those vector addition or scaling would go beyond that confined space. And hence the properties of vector space would break, right? And that's what you see here. So this cannot be a vector space. This entire set cannot create a vector space.
Got it. Thank
Let's
you.
go to second. Second is who? RH. Rutu, go ahead.
I think it's showing for me, sir Naveen. It was
No?
showing one was for, I can see hand number one.
Okay, okay, right, right. Okay, go ahead, go ahead.
Yeah, yeah, sure. Yeah, hi. Hello, sir. So, quick question on scaling. So, there are two questions I have. First is, by scaling, what do we mean? So, I understand the scalar multiplication part.
Mhm.
Uh, can we also have a scaling based on addition of two vectors or matrices? or scaling is only relevant for multiplication, or rather precise to the scalar multiplication?
Okay. When you talk about, actually, there is a term that we are going to learn next, which is called as linear combination. Okay. Linear combination basically takes into account two things: scalar multiplication. uh, I'll write SM from next time on multiplication, sorry, and vector addition. Okay. Now these two things are the basic building blocks for addition, for going to any new place in the entire space. When I say going to a new place, linear combination, when you think about scalar multiplication, you can scale any vector. Okay, firstly, let's say that this is your two-dimensional space. I am still talking in two-dimensional space because it becomes easier for us to visualize it. Let's say that this is a two-dimensional space and this is the vector. When you scale the vector, it can go up here, it can go down when you multiply it with a negative value, and this is the entire zone that it can be, because when you multiply with a scalar number, it can only stretch, the vector will only stretch in this, in on this axis, right? But it can go, not go beyond anything beyond this space. So let's say we call it as a vector. Okay, and we are multiplying it with lambda. We call it as lambda a as a scaled vector. It can go here, or it can be here, or it can be here. Then we have vector addition. Okay, now vector addition is when you have two vectors, you can add them together. Now think of, there is a vector b. Okay, let's say that this is the b vector. Now this particular vector b is, we can scale this vector as well. It can go here up to this, any point on this axis. If we multiply vector b with a positive number, it can go up in this direction. If you multiply it with a negative value, it will be here where my cursor is, right? So it can go in this direction. But when we add, let's say we multiply it with lambda 1, we multiply here with lambda 2. When we add them together, lambda 1a plus lambda 2b, we get to see a new vector. Okay, let's say for example, we have multiplied the first vector and it has resulted here. We have multiplied the second vector with a negative value, it has resulted here. Now because of these two, when we are combining lambda a with lambda b, or lambda 1a plus lambda 2b, we'll get a new vector maybe somewhere here. So this is our new c vector, which is a combination of the two vectors. So we generally in linear algebra, we combine, multiply vectors and we add them together to reach to any new place. This is called as a linear combination. So this is what we eventually do in this entire space.
Okay, so even the vector addition I can say as a scaling, right? Along with the
Vector
scalar
addition is
multiplication.
vector addition is
So this
not
is
scaling.
also okay. So scaling, when I say scaling, it always is a multiplication, which is a scalar
Multiplication,
multiplication.
right?
Scalar multiplication, right?
Right.
Okay. Okay. And a second part to it, the example that you gave last year asked question, minus one, one. So can I say and limit my scaling? So for the same question, like first of all, is the limiting of a scaling is a concept, or no? We can have infinite scaling.
We can have, so if you can limit the scaling, obviously, this is what I thought someone would say, then thanks that you're saying this. If you also limit scaling, okay, then also it will never, let's say, even if you limit scaling and you limit the vector addition, then this can be a vector space. But let's say if you limit scaling, okay, you have vectors. For example, I'm just giving you an example. Let's say that you have vector zero point 0.5, zero point 0.5, and you have another vector, let's say minus 0.5 and minus zero point 0.5. The only thing that you can do is you can multiply it with the scalar number can only be between lambda. Let's say that it can be only from minus 1 to 1. You can choose it in between these ranges. Then also, if you think about, if I multiply it with 1, and if I multiply this one with minus 1, in this particular case, this would be at the horizon, right? But think of it as when you have three, now, right now what you have is two. Now let's say we have three we had that associative property, right? A plus B plus C. we have combined B plus C. For example, let's say this is B, this is C. Now, as soon as we combine it A, this has already gone up to 1, 1. Any addition to it will move it way beyond the space, right? So if you add any new vector to this added number, it will go beyond this space. So that confined space, even if you limit your scaling number, there are chances that that can happen, that your vector will go beyond it. Now think of it as you have one vector as zero point 0.9 and zero point 0.9 and the other vector as zero point 0.5 and zero point 0.5. Okay, and let's say that we scale them only with 1 and we add them, then also it will go beyond 1.4 and 1.4, right? This is not
Makes
within the
sense.
limit.
Makes sense. Yeah. So it is, so basically it has to be a large group rather infinite group for sure. Okay, that answers my question. Thank you, sir.
Okay. Next second is who? First.
Yeah,
Yeah,
hi.
yeah, yeah.
So, it would be great if you could expand a bit on abelian and what relevance does it have on this vector space? It didn't make much sense to me.
There are certain operations which actually abelian group are uh, they were brought into consideration because people realized that while defining the linear algebra they needed vector spaces, and for defining vector spaces they needed group. Now when they needed group were having only those four properties, but there is commutative property which is order. Let's say, how do you combine things, a times b, or let's say b times a, let's say this one. When you combine them, it works well with scalar numbers. When you say 2 times 3 is equals to 3 times 2, or 2 plus 3 is equals to 3 plus 2, this all works well with scalar numbers. Okay, this actually also kind of is okay with vectors. But when you go to matrices, when you scale to matrices, when you go from, let's say, from a scalar, you add two scalars, it becomes a vector, right? So when you have, let's say, two different dimensions of scaling, it becomes a vector. When you have vectors all combined together, it becomes a matrix. Okay, and matrix gives rise to tensors, and then higher order tensors, and so on. This is how the entire thing is. But groups are valid for scalars and for vectors. When we went ahead and found that when we multiply matrices multiplication was failing that associativity order. Like we had that A times B and to C, right? And which in group we are saying that A, B, C is equals to A times B times C. We said that it doesn't matter how you combine them. That is one of the associativity is one was one of the properties of the group. Now, when we move to matrices, we found that we cannot say this to be true for matrices. Okay, because as soon as you multiply two matrices and then multiply it with the result in another matrix C, the output is not going to be the same. Matrix multiplication is not commutative. It has to have a certain order because matrix multiplication is kind of an action. I told you that matrix multiplication, they distort the space. They can stretch, shear, rotate, flip, whatever they can do, but this is your input space. In first space, you can actually distort it like this, right? And then you can rotate this entire space. In the second one, you are saying that you can rotate first and then distort. So obviously the output is not going to be the same. Now, because we had to play with matrix in linear algebra, and think of it as your entire data is nothing but a matrix, right? Whatever you have as an image, or you have a structured data about house prices or loans or XYZ or Spotify premium or Netflix data, what you're viewing with the, it's all structured data. It defines you as row vectors, all the users as row vectors, features as the columns, right? It becomes a matrix. Now, as soon as it becomes a matrix, you would be doing some transformation or playing around with this matrix. Now we are saying that all the moves that we are doing with matrices, they have to obey certain law. And because the other law that we had for groups, it is not being obeyed, we created a new group altogether. We call it as abelian group. Okay, just to make sure that matrix multiplication is it follows the commutative non-commutative property wherein ordering matters. Hence, we created a new thing. We said that there are abelian groups and non-abelian groups, just to keep matrices within the limits. That was created just for the matrices. That's all.
So matrices are not a part of abelian group because they don't follow the commutative and associative properties.
Right.
Is my understanding correct?
That's
Okay,
right.
okay. So it's only the two properties which are part of probably like the scalars or the vectors for it to be an abelian.
Right. So scaling and vector addition.
Okay,
And and
okay.
and and abelian group are they are groups, just that the four axioms of the groups are applied. Just that one more axiom which says the commutative or ordering also has to be respected, but that is already there. If you think about when we were looking into associativity, we said that we combine A cross B cross C, it's exactly same as A cross B cross C. So we were already saying that in terms of associativity. It's just that because we realized that this cannot hold true for matrices, we said that will possibly simplify it. We say that ordering needs to be important. So if we combine A and B, it is equals to B and A. We call this as commutative property, or order doesn't matter. But if the order matters, then we say that group as non-abelian group. So this is an abelian group where order doesn't matter. Okay, sorry, this is equal. But if the combination says order matters, then we have non-abelian group. And matrices form under, matrices are considered as groups which are non-abelian groups. That's all.
Okay, okay, okay. Sure,
Okay.
sure. Yeah, thank you.
Who is next? Aditya. Oh, sorry, Gaurav. Go ahead, Aditya. Yeah.
Hello. Hey, so you mentioned that origin needs to be part of the space, right? So in this case, my origin will always be 0, 0. Means I understand that it can be within space or not, but origin will always be 0, 0 here, right? Or it can change as well.
This. In this two-dimensional space, it would be 0, 0. In three-dimensional world, it would be 0, 0, 0.
Zero. Yeah.
And then n-dimensional world, n zeros. But this is the concept of origin is, let's say, everything that we'll be doing. Let's say, for example, whether you represent an image with a vector, like say this is an image, this is an image of your house, and let's say this is an image of your pet. How would you distinguish that these two images are different? You will have to represent them as vectors, right? And then there has to be some way in which you say that they are different. So you will have to have a reference point. Okay. Because this is inclined in this direction to from the reference point. This is inclined in this direction to from the reference point. Hence, you will be able to distinguish them because you have a reference point. If you do not have a reference point, you will never be able to distinguish vectors. So that's why origins are always important, or the zero vectors are always important.
Thank you.
Next.
Sir, given
Hello.
talking about vector space,
Mhm.
given all scalar multiplication should be in space, right? Does that not mean that we can only have one vector space in any given dimension?
I couldn't understand that. So please speak again.
So, sir, every scalar that I multiply, right, should fall within the space itself, right?
Right.
So that has to be always has to be infinitely long space, right? That could only be
Right.
one of the vectors, one space only, right? I cannot have
Right.
multiple space within one dimension, whether it's 1D or 2D or 3D.
Right. Right. That's right.
So I cannot bound. Essentially, we
You
cannot
cannot
bound
bound. You
any space.
cannot
Any bound
exactly.
space is not a vector space.
Exactly. Now, you cannot bound the space. As soon as you bound, there are chances that when you start doing scalar multiplication and vector addition, those things will go out of those bounds.
Sure. Okay. Thank you, sir.
Hello, Saurav sir. This is Gaurav here.
Yeah.
Am I audible?
Yeah.
All right. Yeah, I think I have a follow-up question with respect to this limiting of the space. So if you could go back to a diagram where we have x within -1 to 1 and y also within -1 to 1. So within that space, we could have infinitely many numbers, right, in decimal spaces also. So,
Right.
and when we have to satisfy those three properties that you have just told that, okay, it should satisfy the commutative property of addition and then scaling, and origin has to be a point in the space. So
Right.
I'm just randomly, if I just take a vector, let's say 1 cross -1, and
1 plus -1. Okay. Let's say that this is your vector.
and if I have another vector, let's say minus zero point 0.1 and
Minus
0.1.
0.1. Okay. Minus 0.1 and 0.1.
Yeah,
Yeah. Let's say that this is that vector. Okay.
it
These
will be
two are
on
the
the
vectors.
minus
Minus 0.1 and 0.1, right? So this
yeah,
is
yeah. So it's like opposite. Let's say x is, if it's positive on the first one, then it's a negative. So it will satisfy both the criterias, right? So if it's like 1, 1 plus minus 0.1 comma 0.1, it will come around 0.9 and minus 0.9, right?
No, when you were talking about specifically about vector addition, but think about scalar multiplication. When you
Yeah,
scale
even
any
if
vector,
if I scale, how much would it come if we
let's say 1 1. If I scale 1 1, let's say minus 1 minus
one
1,
no 1 comma minus 1,
1 comma
and
minus
then
1.
and
Think
the
of
other
it
one
as
I
if
take, yeah.
just concentrate on this vector. If I scale it by 4, it will
Hmm,
go to 4 and minus 4, right?
hmm, hmm, hmm.
So 4 and minus 4 is way beyond this entire space. It will be somewhere here. This is 4 and minus 4 maybe. So this is outside the space. So you even don't have to think about the second vector. The first vector, scaling of the first vector itself is outside the space.
All right.
Right.
Okay. So we don't have to consider the second vector at all in this case.
You don't think about it because the first property that I wrote here is scalar multiplication has to be enclosed. Now you took the first vector, scaled it, and you found that it is already outside. So why would you go to the second vector and say that, okay, let me think of whether it will go outside or not? If the
So
first property itself breaks, yeah,
if
go
I
ahead.
multiply by minus 0.1, scale it by minus 0.1,
Mhm.
so that would give me how much? Minus 0.1 by
You can
0.1, right?
what I'll suggest is you
Oh,
think about it,
mm.
think more about it, and you will be able to find that out. There are n number of combinations. There are infinite combination wherein you can stay within this.
Yeah, correct.
Okay.
Correct.
But then
Correct.
there are infinite combinations that you can go outside this as well. Okay.
Right.
Because
Right.
there are combinations that you can go outside, hence you cannot call this as a vector space. You have to have, there has to be no combination which goes beyond this space. If there are
Oh,
infinite, there are too much, right? So there
all
has to
right.
be no combination which goes outside this space.
Okay. Clear. Thank you. Thank you, sir.
Next is whom?
Hello everyone. Hi Professor. Good morning. Am I
Morning.
audible?
Yes.
So far, whatever we discussed about vector spaces, the crux of it says that vector space has to be infinitely large. Uh, and I mean, in real world or in linear world, is there any example where we could have a limited vector space by restricting the operation that we are doing, like vector addition or scalar multiplication, by applying some rules to it so that it always stays inside that limited vector space?
There are nothing of that sort. That can never happen.
Okay,
That can
so I
never
mean,
happen.
we have to always assume that the vector space is
That's
the infinite
infinite.
space.
Exactly, right.
Okay, got it. Thank you.
And this is a good suggestion, I think, from Himani. Let's take all of those questions because we are going beyond our time. So let's see. Yeah, go ahead, Sayan. I see that you have raised your hand multiple number of times. Go ahead. This is the last question that we have.
Yes, sir. Thank you so much, sir. So just a basic question related to the groups, right? So up until now, whenever we have talked about groups and the axioms, satisfying the various conditions, we have talked about addition and multiplication. But let's say the binary operation in a case is division, right? And so in this case, definitely the axioms is going to, not be followed because we can have decimal values. Right. So can we say that, whenever we have a group defined, we'll also define the respective binary operation associated with it?
Yes, yes. The group, when we say group is considered of two things. One, the set, and second, the binary operation. Okay. Both of them in totality give rise to a group.
So we
Okay, you
also
can.
specify the binary operation
Yes,
which we're
yes.
using.
We
So
also
addition
specified the
multiplication.
binary operation. Yes, that's right.
Okay, got it. Thank you, sir. Yeah.
Okay, let's get into the next part, and I'll mute all of
Sir,
you for the next. Yeah, go ahead, go ahead.
sir, my name is Mohit. My question is the same question I want you to understand. When we say in the group's binary operations, we need plus, minus, multiply, and divide.
Mm-hmm.
And if I take any group where the numbers are like 2, 4, I divide 2 by 4, the answer will come 1 by 2, it will be 0.5. Then will it be part of the group or not part of the group?
See, if you have considered this as uh, the list of integers that you have or list of natural numbers, and you see that the output is already a integer or already a natural number or whatever, there are different types of categorization of these numbers, right? So if the output is still the same as your inputs, then that is a group. If the output changes, okay, let's say for example you are talking about whole numbers but output changes to a decimal number. Okay, in that case, your entire property of the group is changing because whatever we are saying, think groups as simple. Let's say you have a tile, a square tile in your room, right? Whatever you do, all the moves that you do, it has to remain a tile. It cannot become a cube. If it becomes a cube, your property of group is distorted. Okay, so that's how it is. So
Right.
don't think about.
One more thing, sir. For
Mhm.
example, I have a set where I have number 2, 4, 6, 8, something, something. I divide
Mhm.
four. I divide I have set of 4, 5 numbers in which they are integers. I divide one integer by the other number, and I get another integer. But that integer is not already part of that five number set. Then that number will be considered as part of group or not?
No, no, because you're saying that the entire group is only those 4 5 numbers that you have considered. So
Correct.
output is outside that. So you will not say that it is a part of the group, or it will not say that
Oh,
it is a group at all. Okay,
okay. Okay. Thank you, sir.
okay. So let's get into the other part now. Is it got? Sorry, I think I placed the wrong button. Okay, let's get into it first. Now I'll come back to Mohit. What you can do is you can text me. I think we have wasted, not wasted, but at least we have took a lot of time in discussing all of these things, and I have to cover some of the other things as well. Okay, from vector spaces, we are going to go into linear combinations now. Okay. So we are going to learn about linear combinations, and these linear combinations, they obey only the two things that you have already learned. First, vector addition, vector addition, addition, and scalar multiplication. So all the things that you do in linear algebra, they are basically the output of these two things that I have written, scalar multiplication. Every single thing that you will see in linear algebra, they are basically are there because you have vector addition and scalar multiplication. These are the basic two operations that we have. When we when we scale vectors, okay, when we scale vectors, you get a new vector, and that's what you saw here. This is where I was showing you. This is when you scale a vector, you get a new vector. Let's say if I choose any new scaling number, you see that how does the vector scales. But the vector has its own axis. Okay, this vector cannot go beyond its own axis. You are able to see its axis, right? It is whenever I am scaling it with a positive or negative number, even with a decimal or integer, whatever I'm doing, okay, I am not going beyond that axis of the vector. Okay, the scaling has that property that it cannot displace a vector's axis. Okay, is by scaling you will not be able to just move this vector to a new point here. You will have to have it on its own axis. That's scaling does. When we add vectors, let's say we have the first vector, we can scale that first vector like this, right? And we have the second vector, we can scale the second vector like this. It would be always on its scale, on its axis. Now, when we scale two vectors and add them together, now let's say what we scale this vector, we scale this vector, and then we add them together, then we would always be getting a new vector altogether. See here, right? See all the new positions that this vector is able to traverse to. Now think of this as your park. Okay, this is the park that you have, and you are not bounded to go anywhere. So you can travel to any point. You can take steps. You are starting from here. You can go to this point. You can go to this point by obeying the decision, saying that you only have to walk. Right now, these vectors are doing the same thing. They're saying that there are only two rules. You can scale yourself. These two vectors can scale themselves, and then they can add them together. If we scale them, add them together, this is the new point. Now, if we scale the blue vector, these are the set of new points that you see, right? Now it is all able to scale, get to the new point. Now, these new set of points that you are able to cover, these are called as linear combinations of vector A and B. So linear combinations are nothing but a set of new points. Think of linear combination, a set of new points that you are able to cover when you scale vectors and add them together. Good? Good, right? I mean, when you scale vectors and add them together, you are able to just reach to few new points. That's all, right? So these are called as linear combination. Linear combinations are nothing but new positions that we have got by just scaling and adding vectors. Okay, and that's what you saw on that side. So you are scaling vectors and adding together, you're getting to the new points. So these are called as linear combinations. But are there vectors now think of it as if these two vectors would have been exactly at the same axis. Let's say that vector A is also, or vector B is also on the same axis as of vector A. Now, if I scale vector B, okay, do you think we'll be able to scale all possible points, or we'll be able to reach all possible points when both of these vectors are on the same axis? Let me show it to you here. Laptop is getting heated up. Just a minute. So let's say that this is what we have. Okay, let's say that we have the first vector, which is 1 2. Let's say that this is 1 and 2, and let's say that we have the third vector, which is this one, second vector, sorry, which is 2 4. Okay, let's say that these are the two vectors that we have. Now 1 2 obviously is a scaled version of the first one. So we had the vector 1 2, and we have the new vector as 2 4, right? Now, if you think about, if we scale these two vectors, let's say if I multiply the first one with 2, the second one with 3, if I add them together, what would be the output? The output would be 2 plus 6, 8, right? 2 into 1 plus 3 into 2, 8. 4 plus 12, 4 plus 12 is 16. So we'll get to 8 and 16. Now think of where that 8 and 16 would be. 8 and 16 would be somewhere here on the same axis. Let's say that this is 8 and 16. Now, what you have just realized, when you have vectors which are on its own axis, on the same axis, whatever, no matter with whatever number you can scale them, they will always remain on that same axis. Okay. Now, these vectors, which are on the same axis, these are called as linearly dependent vectors. Okay. So, these two vectors right now, 1 2 and 2 4, These are linearly dependent vectors. Okay. You understand it why? Because if you think about, if you multiply 1 2 with 2, you will actually get to 2 2 4, right? So if you multiply it with 2, you will get to 2 4. Or you divide the second vector by 2, you will get to 1, right? So both the vectors are just scaled version of each other. When the vectors are just a scaled version of each other, then they are called as linearly dependent vectors. Okay, this is the first condition of linearly dependent. So we are discussing about linearly dependent vectors. Linearly dependent vectors are those vectors which can, let's say right now we have just discussed, if we can scale vectors and still we get the same vector, then those set of vectors are called as linearly dependent vectors. Same goes with, let's say we were discussing about two vectors. Let's say we have a set of three vectors. Okay, let's say we have 1 2 2 4, or let's say 1 2 3 5, and let's say 4 and 7. Now, in this particular case, if we can add these two vectors, if you think of, if we can add the first vector A, the second vector B, if we can add them together, I will get 1 plus 3 is equals to 4, 2 plus 5 is equals to 7. So if I can add these two vectors, I get to the new vector, which is 4 7. Okay. So linearly dependent vectors are nothing but a set of vectors that can we get by combining these two vectors, original vectors, right? So let's say if I multiply the first vector with A, the second vector with B, so all the vectors that I can generate by combining them are called as linearly dependent vectors. Let's say on the right hand side, whatever we get right now, A is 1, B is 1, I get 4 7. But if A is equals to 2, B is equals to 2, I'll get something else. Okay, whatever I get, let's say 2 plus 6, 8, and then 4 plus 10 is 14. So I'll get 8 and 14. Okay. Similarly, I can get all the other set of vectors by combining them. So all the other set of vectors which gets combined, these are called as linearly dependent vectors because the output is linearly addition of the input vectors. Scaling those, if you think about, this is scalar multiplication, this is scalar multiplication, and then we are doing adding, right? Scalar multiplication and vector addition, all the set of vectors that you can generate, they are called as linear combination. And linear combination can have set of vectors which are dependent, right? So linear combinations are nothing but a set of dependent vectors which gets created because of your input vectors. Okay, now think of as when you have a set of vectors, can you call them as dependent by looking at them? Let's say, for example, when you have 1 2 and 4 8, you can already say that by looking at them, you can say that okay, these are dependent because the second vector is nothing but 4 times of the first vector, right? So they are linearly dependent because you can scale this vector and get to this point. So these are linearly dependent. Now, there is a mathematical way of writing that. Okay, this is the linearly dependent vectors, mathematical way of writing linearly dependent vectors. So if you have, let's say, a set of vectors and you can combine them as in scalar multiplication. Let's say lambda 1 times a1 plus lambda times these a1 a2 are vectors, say lambda 2 times a2 plus lambda 3 times a3 plus and so on plus lambda n times an. Let's say there are n vectors, n scalars, you are just scaling and adding them together. Okay, if you get to see that after adding them together you are combining them to 0, it means that the vectors are linearly dependent. Okay, what do I mean by that? I mean, this is a formal definition of linear dependence. But what do we mean by that? Think of more intuitively. Let's say we consider only first two. Okay, what we are saying is lambda 1 a1, okay, plus lambda 2 a2 is equals to 0, which means that you can say that lambda 1 a1 is equals to minus lambda 2 a2, right? Now we can also say that A1 is equals to minus lambda 2 by lambda 1 into A2. So if we have anything of that sort, you already know that if we can write a vector like A is equals to 4 times of A2, then they are dependent. You already saw that. We already saw that both the vectors are dependent, right? So in this particular case, they became independent. They became dependent from the first two. Same can be deduced for the third one. Let's say, for example, we are considering the third vector, lambda 1 a1 plus lambda 2 a2 plus lambda 3 a3, okay, is equals to 0. You can actually write like this: lambda 3 a3 is equals to minus lambda 1 a1 plus lambda 2 a2. Or what you're saying is, when you scale the first vector and scale the second vector, add them together, multiply with the negative sign, you or negative number, then you are getting lambda 3 a3. Or you can say that a3 is nothing but minus lambda 1 by lambda 3 times a1 plus, or sorry, minus lambda 2 by lambda 3 times a2. So basically you're saying that a vector is a linear combination of input vectors, right? Why I'm saying linear combination? Think of lambda 1 by lambda 3 as c. So you're saying that c times a1 and lambda 2 by lambda 3 as d, or minus lambda 2 by lambda 3 as d. So c times a1 d times a2 is equals to a3. So if you can combine these vectors and get to a new vector, that is a linear combination. And this particular vector is called as dependent vector, because A3 is dependent on how you combine them, right? So the only way to express linear dependent vector is this, okay, which is lambda 1 A1 plus lambda 2 A2 plus and so on lambda n an is equals to 0. If you have a way of combining them such that not all lambdas, now this is the interesting thing. If you can combine them such that they become 0, they can add up to 0, it means that they are linearly dependent. But the only way to combine them and make them to 0 is that these lambdas, these scalar things are 0. Then the vectors are called as linearly independent. Okay. So the only way that they can combine and become 0 is when these scalars units, these scalar values become 0. If these scalars become 0, then if that is the only way to combine them and make them equals to 0, then that is linear dependent. Now, I'll give you a simple example for that. I mean, I'll come back to your questions, but I'll give you a simple example of that. Think of these two vectors, 0, 1 and 1, 0. Think of, can you scale this vector and get to this, or can you combine these two vectors, or make to the next vector? Are these two vectors, firstly tell me, are these two vectors linearly dependent or independent? Can you scale the first one and get to the second, or scale the second one and get to the first? Are they dependent or independent? Independent, right? These are independent vectors. These are two vectors which are independent in this entire set. Okay. Now think of as uh, using these two vectors, because these two are independent vectors. These are the two vectors that we have plotted. First, 1, 0. This is the second vector, and this is 0, 1. This is the first vector. These are the two vectors that we are talking about. Okay, and both of these vectors are independent. You are able to see that they are independent because they are not on the same axis. Okay, firstly, the first visual way of saying that is they are not on the same axis, they are independent. But you can visually see them right now that both the vectors are independent. When you have a set of independent vectors, you can also say that the only way to combine them, lambda 1 times 0, 1 plus lambda 2 times 1, 0 is equals to 0. The only way to combine them is to make lambda 1 and lambda 2 0 to make the output as 0, or to make the output as 0 vector. Okay, or let me write it as 0 vector, 0, 0. Okay, the only way to combine them and make them 0 is You cannot take lambda 1 as 1 and lambda 2 is equals to 0. The only way they can become 0 is you take these two as 0. And then you will get output as 0, 0. Because this is the definition that we created, I'm just giving you a point how to justify that definition. The definition is for a set of vectors to be linearly independent, the only way to combine them is by making sure that these scalars are 0. Then they are called as linearly independent. If these scalars are non-zero and then you're able to move to 0, it means that they are linearly independent. For example, let's say I gave you two simple examples, 1 2, let's say, and 3 5, and the output is 4 7, let's say. Okay, whatever you do with these two, you can just simply write it as lambda 1, lambda 2, and lambda 3. Let's say that lambda 1 times this, lambda 2 times this, plus lambda 3 times this. You know that there are these lambda 1s, lambda 2, lambda 3s, and what these lambda 1, lambda 2, lambda 3s are. You can find non-zero lambda 1, lambda 2, lambda 3s. For example, lambda 1 can be 1, lambda 2 can be 1, and lambda 3 can be minus 1. Okay, when you add them together, you will get to 0. Let's say, for example, 1 plus 3 minus 4, you have 0 first, right? 2 plus 5 minus 7, 0 there. So while combining them by not necessarily making all of them 0, you are able to get to 0, right? Hence, these are called as linearly dependent. The other intuition of linear dependent is if the vectors are on the same axis. You think of 1 2, this is 1 2, for example, you will find out that 3 5 is also on the same axis. Okay, if the vectors are on the same axis, they are linearly independent. This is the scaled version. But the other way of writing linear dependent is, let's say this is a first vector 1 2, and there is another vector, let's say minus 1 and 2. And if you add them together, minus 1 2 1 2, if you add them together, you will get 0 4, right? And 0 4 would be somewhere here. Now, if you can add the vectors and get to the third vector, that also is a linear dependent. So we are saying that 0 4 is linearly dependent on these two vectors. So it's not like the vectors which are on the same axis, they are linearly dependent. If we can scale and add the vector together and get to the third vector, then it also means that they are linearly dependent. This is visual way of doing that, understanding that. But the formal definition is you have this lambda 1 times a vector plus lambda 2 times a1 vector, a2 vector, plus and so on, plus lambda n times an vector. If you add them together, and the only way you add them together is by making all of these lambda 1, lambda n's 0, then they are called as linearly independent. If you add them together such that lambda 1s, lambda 2s are not necessarily 0, but you are still able to get to 0, then they are called as linearly dependent. Okay, so this is linear dependence independence. Now I'll just cover two more topics. After that, I'll open up for you. I know that I have only 12 minutes. That's why. Okay, and then you can stay for 10 more minutes and then we can discuss about it. Think of it as linearly independent and dependent vectors give rise to two new properties. One is called as span. The other one is called as dimensions. Okay, span is when you have linearly independent or whatever set of vectors. Span is which new vectors can you create or get to by linearly combining vectors. Linear combination is scalar multiplication and vector addition. Okay, when you scale vectors and add them, what are the new positions that you are able to get to? Okay, that is called as a span of a vector. Now, a span has, let's say, for example, if the vectors are dependent, for example, here, if you think of, this is what is called a span. Now, think of if these two vectors are not dependent. Okay, now you are able to see all of these shining stars of different colors. These are the new positions that you can get to by just scaling these two vectors and adding them together. Okay, these are the new set of points. All of the entire, let's say this is two-dimensional space, right? This is a 2D space. Now, if the vectors are independent, these two vectors are independent, v1 and v2, they are not on the same axis, right? Both of these vectors are independent. If you can scale and add these two vectors, you can actually exhaust the entire two-dimensional space. You can reach to any point on this two-dimensional space. But on contrary, if these two vectors are somehow dependent, you will never be able to go beyond this entire axis. Now think of, I told you Carl Sagan's statement. He's a scientist, space scientist, and he once said that we, the beings of three dimensions, are trapped in three dimensions. All the things that we can do, we cannot go beyond three dimensions, even though four dimensions or higher dimensions could exist. You might have seen Interstellar and the last scene of Interstellar, wherein four-dimensional reality is captured. Sorry, three-dimensional reality is captured into four-dimensional cube, right? So if you see here right now, these two vectors are linearly dependent. Hence, you are not able to, whatever you do, you scale this vector, you scale this vector, add them together, you will not be able to go beyond any points which are highlighted, getting highlighted. So these are spans of these two dependent vectors. The span of dependent vector would be the axis on which they are. Similarly, let's say, for example, this particular set. When you have independent vectors, you can actually explore the entire space. So a space span basically is what new vectors you can get to by scaling the actual vectors that you have in the set. Okay, this is the first vector, this is the second vector, you are scaling them, adding them together, you can actually reach to any new point. To help you understand that visually, not visually, but mathematically, let's say you have a new vector, you have a vector 4, 7, okay, and then you have a vector 2, 4, okay. If you can add them together, let's say if I multiply this with 2, this with 3, then add them together, I will get to a new vector 8. 8 plus 6 is 14, and 14 plus 6 is 20. So basically, by just scaling the first vector and scaling the second vector, adding them together, I am able to get to a new point, which is 1420, right? So this is in the span of these two vectors. This is basically a new place that these two vectors can exhaust, or these two vectors can actually reach to by scaling themselves and adding them together. Right now, you can scale them as like 5 and 20, and you can reach to any new point. And that's what you were looking at on the visual thing, right? Now, when you have independent vectors, let's say for your two-dimensional space, when you have independent vectors, let me draw it clearly. Let's say that this is how it looks like. Okay. This is your first dimension. This is your second dimension. Let's say that the vector is 1, 0, and the second vector is 0, 1. Okay. Now, when you have linearly independent vectors, okay, and using those two vectors, if you could reach to the entire, you could exhaust the entire space, then those two, the entire space is called as span, but those two vectors are called as basis vectors. Basis vectors are basically independent, linearly independent vectors using which we can exhaust the entire space. Okay. So if there are linearly independent vectors, so basis for vectors to be basis, there are two important things which are I'll share it with you. There are two important things which are important. First, they has to be linearly independent, linearly independent, independent, plus they have to exhaust the entire space, or they have to span the entire space. If they can span entire two-dimensional space right now, because we are considering two dimensions. Okay. So if the vectors are linearly independent, this is the first thing to consider. And if they can span the entire space, both of them can happen using those two vectors, then the vectors are called as basis vectors. Okay. Now the number of vectors in this basis vectors are called as dimensions. Right now we have, let's say the set has these two vectors, okay, 0 1 and 1 0. Okay. Now, these are firstly, these are linearly independent. You already have stated that. Using these two vectors, you have also seen that. Let me also show it to you again. Let's say that this is the first vector. This is the second vector. Okay. Now, if you have these two vectors linearly independent, you will be able to exhaust the entire space. So you are able to actually reach to any possible point in this two-dimensional space. That's why you see, if the vectors are linearly independent, you will be able to mostly you'll be able to span the entire space. But there are chances that the vectors are linearly independent and they cannot span the entire space. And those chances are, think of this. You have a three-dimensional space. Okay. I know that there are only 5 minutes left. Let's say that there are these are the three vectors that we have. Okay, 1 0 0. This is the first vector, and this is the second vector, 0 1 0. Now let's say that, are these two vectors independent or not? In the set we have 1 0 0 and 0 1 0. Are these two vectors independent or not? Independent, right? They are independent. Now, because these two vectors are independent, they can span some space, right? But can they span the entire three-dimension space? Can they span the entire three-dimension space? No, because the third dimension is also required. Whatever they can do is they will stay in this space. Okay, whatever new point that they can reach to, either this, they can never get outside that. That's why I said we, the beings of three dimensions, are trapped in three dimensions. Always remember that. But anyways, this is what is happening right now, right? These two vectors are independent. They are still not able to span the entire space. That's why for the definition of basis, we had to strictly say this: the vectors have to be linearly independent and they also have to span the entire space. Now, if we add the third vector here, 1 0 0 0 1 0 and 0 0 1, if we take these three vectors, we will be able to span the entire space, right? And how many vectors are there in the basis? There are three vectors, but dimension would be three. Dimension is three, and the basis vectors are these three. So using three linearly independent vectors, we can access the entire 3D space. Okay, and the dimensions are three, because dimensions is nothing but how many number of vectors do you have in the basis. And for basis, what do we need? Linearly independent vectors, and they should be able to span the entire space. Good? Yes, no? What if we have three vectors? This should be good, right? I mean, there are a lot of things that might be overflowing, and I was not able to cover a lot of things that I talked about. But this is what I wanted to cover, and the second part was RREF and particular solution. This is what I'll cover in the next class. I'll unmute all of you for next whatever time that we have, so that we can discuss. But I hope that this class was able to help you understand vector spaces. Why? And one more thing before some of you start speaking, think of it as why this is important to machine learning. The machine learning connection is every single thing that you see in data, whether it is text or image or structured data, they all can be represented as vectors. Let's say this is image number one, this is image number two. You can find out how similar, dissimilar these images are by just representing them as vectors. Because we have vectors in place, we have to define where vector live. Either it is two-dimensional space or n-dimensional space, right? So that's why vector spaces are important. And when we talk about vector spaces, we'll have to talk about where these vectors can actually go to. Hence, we'll have to talk about linear combinations, vector additions, and scalar multiplication. Using those scalar multiplication vector addition, you can actually exhaust either some part of the space or the entire space. If the vectors are linearly independent, there are possibilities that they can span the entire space. Okay. And if they are independent, so if they are dependent, then you have already seen what would happen if they are dependent. Then they cannot span the entire space. You see this, right? This is the only line that they can go to. So you cannot move beyond them. So we are kind of human beings are linearly dependent species. We are just dependent, and we cannot ex mm, exhaust the entire n-dimensional world that we have in the world, right? We can just s- e- live in this three-dimensional reality we are part of, and that's why quantum mechanics is important. Some of you might relate to it at a later point in time, who would do some research in quantum mechanics, and then you will realize that this is one of the possibilities of n possibilities that can exist in the world. But anyways, let's discuss about your questions.
Hello, sir. Sir, hello.
Yeah, yeah.
Yeah, sir. How 1 and 2 plus 3 by 5 is linear dependent?
1 and 2 and 3, 5.
Yeah, the example you gave.
See, first thing is, if you think about 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Firstly is 1 and 2 is this vector, okay? This is the first vector. And 3 and 5 is this vector, okay? So firstly, they are not on the same axis.
Yes.
They are not on the same axis. Visually, you can think of. Now, 1 and 2, if you have lambda 1 plus lambda 2, and I will, in the next class, I'll tell you about how can you, right now you are able to actually find out how they are linearly independent by visually seeing or doing some heuristics math. And next class, when we'll be doing RREF or reduced Euclidean form, you will understand that we can use reduced Euclidean form to find out whether the vectors are dependent or not. Okay. So let's say that this is 3, 5. Now, these are independent if the only way to combine them and reach to zero vector is lambda 1 and lambda 2 be 0. Now, are there any possibilities? Think of all the possibilities that can exist. Are there any possible things that you can have? Let's say lambda 1 can be any positive number, lambda 2 can be any positive negative number. You cannot scale them and add them together to reach to this point. That can never happen. Think of all possible values of lambda 1 and lambda 2. That's why these two vectors are linearly independent. The only way they can become zero, scale and become zero, is when lambda 1 lambda 2 itself becomes zero. Okay. So that's why they are linearly independent. Okay.
So can you go to that example 1, 2, 3, 5, 4 by 7 you gave? Just scroll up.
Just a minute. Yeah.
Yes, sir,
Yeah.
this one. So here
Mhm.
you said it is linearly dependent. How?
Because you are able to see that 1, 2, when you add 1 to multiply 1, 2 with 1, 3, 5 with 1, and multiply -4 and 7 with -1, you would be able to see that 1 plus 3 minus 4 is 0, right? 2 plus
Hmm.
5, 7 minus 7 is 0. Hence, you are able to reach 0, 0 using
Okay,
some
sir.
linear combination of them.
Okay, sir. But in in this graph left side, here you give -1, 2, and 1, 2. This all these vectors are on different axes. So
Right.
how this is linearly dependent?
I'm saying that this vector, the output, when you add these two, you get a new vector here. This is a linearly dependent vector because this got added up, and this we reached there because we combined these two. We
Okay,
just added these two vectors.
if we get 0, 0, then it will be linearly independent.
If we, let's say, for example, you 0, 0 is already linearly dependent vector. It's already dependent on, because this is a part of your axis. 0, 0 would always be a dependent vector. no matter what. The zero vector is always a dependent vector. Now, your understanding of linear dependence and independence is, think of the simplest thing is, when you have a set of vectors, is there a possible way we can just combine them and make them to zero? Okay, if we can make them to zero, combine them and make them to zero. When I say combine them, a1 times, let's say there is a vector number 1 plus b a2 times vector 2 plus a3 times vector 3 plus and so on plus an times vector n. If we can scale them, add them together and reach to zero vector, okay, then they are called as linearly dependent. If you can find out any possible combination, not all of them zero, a1, a2, a3, if not all a1, a2 and a1 are zero, okay, then still you are able to reach to zero vector. It means that you have a linearly dependent vectors, right? Now, by going by the definition, think of it as zero vector. If you can have something of this sort, zero vector is already a linear combination of these vectors. So zero vector would always be linearly dependent, no matter what. It would always be a dependent vector of all the vectors that exist in that space. Okay, so one way of doing that is, this is very hard way. This is, you will have to find out what are these a1, a2 values which makes it to zero vector. That's why I told you in the next class, I'll tell you a easier way. Okay, and that easier way is to find out first the Euclidean form. Once you have the Euclidean form, you find out how many pivots do you have. Those pivots in the column, the columns which do not have the pivots, they are basically the dependent vectors. If we have all the columns having pivot values, the vectors are linearly independent. But if some columns that do not have the pivot value, then the vectors are linearly dependent. That's the only thing that we'll have to do. Other thing is, when you create the matrix out of the vectors, when you arrange all the vectors in a matrix such that this is the first vector, this is the second vector, this is the third vector, if you arrange them like this and you find that the determinant of the matrix is zero, okay, and if the determinant of the matrix is zero, it means that the vectors are linearly independent. And this is what I will show visually what happens. This is called as singularity. When you might have heard about singularity in intercellars, but singularity is when your entire space actually squishes to a low dimension. And there are various different cases wherein that can happen. Okay, let's say here, if you see transform, when the vectors are dependent, let's say that the vectors are dependent, then what could happen is you could get to squishing of space as that moves from 2 dimension to 1 dimension. This is how that would look like. This is how the transformation would look like. So now you had 2 dimensional space has got squished to, or has got resulted into 1 dimension. So if you have this type of space, the determinant I told you is the area, right? The a line doesn't has area, so area becomes zero. Hence, you will see that if the matrix gets created such that the determinant of the matrix is zero, hence that's a singular space. Hence, you vectors are dependent. That's all. But anyways, I'll talk about all of these things in the next class. Okay, and then go through the component docs. It has a lot of things. I have a class in 3 minutes, and I also have to take breakfast. So sorry about it. I'll connect you. You can post your messages or whatever text that you have or your understanding in either to on the WhatsApp or here. But do let me know about what you have understood, what you have not understood. It will help me. Okay. Thanks everyone.